second interpretation that I promised you is their interpretation as neural networks. It's not so much an interpretation, actually, than the neural networks that, as the way I will describe them, are a special case of shape-morphing solutions. In the following sense, in a neural net, in my context, the inputs are going to be the spatial variables, the coordinates of the spatial variable x1 to xd, and the output is going to be my approximate solution. Each node of the neural net, this is a shallow neural network because it has just one hidden layer, but you can generalize this to deep neural nets too. If you look inside each node, usually in neural nets, you multiply the input with a weight function, weight parameter, which is W, this is a matrix, and you add a bias bi here for node I, and then you apply an activation function phi, which could be a sigmoidal function or tangent hyperbolic, for instance. And the output will be this activation function applied to this expression, and then you add them up. This is the output of the ith node, but you add up the outputs of every node with an output weight alpha I. That's in the amplitudes in the shape parameter, in the shape morphing solution. As I had alluded to before, the crucial difference here is that unlike conventional use of neural networks, now the weights and biases of my neural net depend on time. I have to prescribe how these things change over time. Yes?
I'm having a hard time conceptualizing how this is different from training.
As I will explain, there is no training needed in this. I can write down explicitly what are the differential equations that these parameters need to satisfy. I don't need any input into any data in the traditional sense of training, that I don't need input data and output data.
Okay, you still have input data, which is driving the network, and you still have an output, and you're making some decision on how to change the weights and biases based on that.
Right.
So you could technically say you're training the network, right? Even though the algorithm might not be stochastic approximation or whatever.
The training is in the sense that if imagine you have a neural net which has one-dimensional input, one-dimensional output, right? Mm-hmm. Classically, when you train the neural net, you feed in a lot of those one-dimensional observations, the inputs, right? Mm-hmm. The more you feed in, theoretically, the better your neural net performs, right? Here, I have really no observations to feed into this. In other words, my x1 to xd are not really observational data or measurement data or numerical simulation data that I'm feeding in. Hopefully, when I write down the equations of motion for the parameters, it will become more clear. Yes?
You're projecting the dynamics onto the manifold and by the parameters of the neural network. But one question would be, if you have so many parameters and the expressivity of the neural network is so large that basically the same dimension as it's very large dimension, and you're not recovering the intrinsic coordinates of the solution space, and there's no advantage of using this method. So how do you make sure you're approaching the true dimension of the solution space?
I think your question is related to the over-parameterization, right? You don't want to necessarily over-parameterize your network, and I sympathize with you that, yeah, you don't want to do that. The way we work for it, we don't have a criteria that stops you from over-parameterizing. We start with a pretty low-dimensional network and then increase it until we reach a good error tolerance that we're happy with.
So we're trying to get a point that when we increase the parameter, the solution get really bad.
Yeah.
So that's the point.
Yeah. Mm-hmm. Was there another question? I guess no. All right. As I said, this can be and has been actually expanded to deep neural networks.